In this video I create a separate micropython Bing library. This library will use a set of varying length ICMP pings to determine a network's available bandwidth and latency. I've also cut down the ping library used in the previous video. This is so it just performs one ping per request and returning the ping measurements to the calling routine, so I can use it from the Bing library. Making it more streamlined and refining the timing mechanisms for more precise results. I've also used a randomized packet payload to reduce the chance of timings getting impacted by any network compression.
So I made changes to the ping program, the library I downloaded off the internet, and really I just wanted to simplify it a bit, make sure the timings were accurate. This is the new one here, so the good thing about using VS Code is I can use it in combination with GitHub and compare files and things, so I'm going to do that right now. So I'll just look at my Git history. I've got a version here which has the original version I downloaded of ping from the internet, and by right clicking on that I can compare against the workspace version. So this displays the two versions of the ping library, the original and the one with the changes I made in it. And let's just zoom this up a little bit, and I can close that to make it a little bigger. So the one on the left hand side's my current version, the simplified version, and the one on the right hand side is the original version from GitHub. So let's have a look at the changes I made. So first changes was at line 25. I added a routine to generate a random string. So I can pass it the size of string I want, and it returns a random string based on these printable character list of printable characters. Next change I made was around the actual parameters passed to the ping. So this is the original here, where it took the host name, the number of pings to perform, the overall timeout value in milliseconds, interval between pings, whether to print out informational messages as it ran, and the default size. The way I've changed this is really just simplified it for the use I'll make of ping with the Bing routine. So again, just the host name, default size of 16, and then timeout of 5,000 milliseconds still. Let's look at .39. Okay, I added more comments in here about what was happening during the ping. Some of the decisions I made based on looking at the ping going over the network, or the ICMP packets going over the network. One important thing was I saw that if it's below 26 byte payloads, I was getting different length ping packet going over the network, going to the destination and then being returned. Over 26, it seemed to be same size both ways. So again, that's useful to have same size, or know what the same size pings are, because the assumption is that it's getting hit by the same network constraints on the trip to the target machine and on the return. Down at 75 here, changed some of the parameters that were being used. I've got this t elapsed value, so this is the actual value in milliseconds of the ping time. By default I've set it to -1, so if the ping routine fails, I can tell by it still being -1 that the ping routine failed. I've got a finish flag, and then a size on wire. So this is a new thing. I wanted to know what size the packet is that's actually going over the wire. So I've got a variable to hold that as well. I removed a lot of the the code in the original one, because it's doing multiple pings based on the ping count requested. I'm only always doing one ping when I call the ping routine, so I could take some of the looping out of it. So you see here, this is the send packet routine. Some of the things I didn't need a sequence number to increment anymore because I was only sending one ping per time. Also, the way I calculate the timeout, I changed to setting the further down here, I calculate the timeout by setting a timeout value based on the current time plus the timeout value multiplied by 1,000. So that's the actual tick time that represents when the routine should time out. So there's a change from the original routine where it was keeping account of the timeout. Now I compare the current time against the t timeout value and exit when that happens. I think that might be a little bit simpler, more performance. So doesn't also gets rid of the 1 millisecond granularity in the times that the old one would have given you. I think this one actually gets me down to about half millisecond granularity in the times. Let's look at 100. So it's waiting for a response. It's waiting for it to be an ICMP packet type. So this H2 type is looking for it to be a ICMP packet, and then the ID is the same as was set. So a random ID number is set when the packet is sent to make sure that I'm actually looking at the ICMP packet being returned for the actual request that I made. And then finally down here, change I've made is to just return the values that are collected. You'll find if there's been any problem with the ping, so again, if TLapse is still -1, it indicates that it failed, so it'll just return none. Same thing happens up here where I'm sending the packet. If the packet wasn't sent properly, it just returns with a none. Otherwise, it returns with a tuple with the time elapsed in milliseconds, the TTL, so this is the number of or the remaining time to live for the packet, so it can tell you how many hops the ICMP packet took to get to the target, and then the size on wire. So this was calculated from using Wireshark. And to check that that's all working, I'll go with my tester pi. I changed this around a little bit as well, so now I'm just doing 2 pings using my new ping routine. So I'm pinging to the machine I'm on at the moment, and this is going to be a 16-byte ping. Now if I bring up Wireshark and do a trace of ICMP packets coming into this target machine, when I run this code, let's try it out. So I've got 2 pings being reported in my routine, and if I go to Wireshark, I can see the packets arriving at this this machine and being returned. So here's the interesting things, because I was using a 16-byte payload, the size being sent is different from the size being returned. So this is where it could skew the results of my Bing routine, which is the reason that I changed to 26 minimum, at least for when I'm using the Bing routine. Let's just save that, run it again. So I ran it again. Let's look at our packet trace now. So it's being sent as a 60-byte, returned as a 60-byte, and this is going to hold true for all the larger packets. Okay, this is showing the Bing routine. So I've added quite a few files, so I'll be covering some of the other files in future videos, but the one I'm looking at the moment is the Bing routine that does all the calculation of network bandwidth based on the ping results. So just working backwards, this is the tester program now. It's much simplified, just doing one Bing to local address, and then my actual Bing routine shown here. So I'll quickly walk through this. So it's using the ping routine that was cut down and simplified. I'm actually doing an import as, because I have an alternative ping routine for testing. See here, there's a one that all it does is return results without actually going out onto the network, so I can check that the Bing routine is working correctly when I have CAN results that I return, and I can use that just by changing this to a underscore. So I've used the alternative uping library, but for now I'm going to use the network-based ones. So the actual Bing routine, there's some comments in there, but what it's doing is for 5 different addresses, or combination of addresses and ping sizes, it's using a routine that I've created, and I'll get back to that, called get lowest ping. So the first one's just purely to get latency, so it uses the absolute lowest ping that my ping routine supports. So it's using a 16 byte packet payload for the ping, just to get the lowest latency it can record. This get lowest ping actually does multiple pings, whatever I say is the number of samples, and just returns what was the lowest pings, because the lowest ping should be the best possible result over that network connection, which is usually what I want with a Bing, is to find the best actual bandwidth at that time. Then getting into the samples I need for working out the bandwidth is I get a lowest ping result for a loopback address of the minimum symmetric ping of 26 bytes payload, and then the same thing, I get the lowest ping for the largest ping size I can support at the moment. It gets passed as max size, and the same thing for the actual target that I'm testing. So these loopback ones are used to get a baseline for what the ESP32 time it takes to do pings, and then these ones, the actual target, will include that baseline, so I need to subtract it when I'm doing the calculation. I've got a whole lot of checks here to make sure that the results I get will make sense for calculation. No point doing a Bing if things like the large packet size returns faster than the lowest one. I know the result's going to be wrong. And again, with the ourProbes, it's really just looking for trends, and if it can't do a good Bing at a certain time, I just throw out that result. So I'm fairly tight on what it'll accept as results of the pings. And then the actual calculation, so it works out the delta latency. So this is where it's using the loopback information. So the delta latency is the target max minus the loopback max, and then minus the target small ping size minus the loopback small ping size. So that's the delta latency when you take out the baseline for loopback. And then the other calculation it's doing is the delta payload bytes, which is the max size of the samples minus 26 times 8 to change it to bits, from bytes to bits. And then the actual calculation bits per second is what we looked at in the previous video for the calculation. So it's 1000 divided by the delta latency, so that just puts it in the second scale rather than millisecond scale. The delta payload bits, then times 2, because we're actually measuring the bandwidth constraint both ways, seeing it's a round trip for getting the ping latencies. And let's just run back and have a look at this extra routine it's using. is get lowest ping. Takes a host name, number of samples to do. So the more samples, the more chance of finding out what is the absolute consistently lowest ping size I'm seeing. I've been experimenting with different numbers, but I think somewhere between 5 and 10 is probably what I'll use in most cases by default. The size of the pings to do, the timeout, and then whether to print the results, print the debugging information. So at the moment I've got it set to false, but in production we'll set that to true so we don't get a lot of printouts as this thing's running. And then it creates a list of pings to hold the ping results, and then for each of the pings to be performed in the whatever number of samples I've asked for, it gets the ping result, appends that ping result to the pings, does a printout of the ping result, and then it does a quick run through of those ping results to find out what's the lowest one, and I'll report back on the lowest one. If there's more than 2 failures in the samples, so say we do five pings and 2 or more of the samples don't return or time out, then it's just going to return none. So that's going to be one of the cases where it doesn't try and calculate the bandwidth, that the ping samples aren't good enough to do that. So we're all set. So again, just using my PyCon console down here, I'll upload that whole project to the SP32. I'll go over to my tester routine, and again you see it just sets up a network connection, sleeps for 2 seconds, and then does our ping routine. In this case it's doing it with five samples per to get the last result. And we should see it getting printed out down here. So let me run it now. So we're connecting to the network as .69. It's doing pings to a local machine on the same network, but remember it's going over to Wi-Fi. It's getting all these ping results. Looks like there weren't any problems with the results it got back, so it's got a delta latency of close to 2 milliseconds, delta payload bits of 11,472 bits. So it calculates the bits per second as close to 10 megabits per second. We can try running this away one more time just to see how consistent it is, but looks like my ping routines, or my Bing routines, working and returning bandwidth numbers. Okay, this time it measured about 5 megabits per second. I'll try it one more time. And again, there's going to be some jumping around in recorded bandwidth, which is normal for a network. So this one's about 5 again. So if we look at this over time, which our pros will allow us to do, we can sort of see how consistent those bandwidth numbers are. If other things are happening on the network, you could find cases where there can be magnitudes of difference in bandwidth, which is kind of what you want to find out, but you'll see sort of general trends of what it's capable of. The other thing to remember is this has a maximum ping size at the moment of about 1460 bit payload. It'd be good to be able to do larger ones. At the moment I'm restricted because the network stack on the ESP32 doesn't seem to support fragmentation, so later on I'll dig in and see if I can support fragmentation, which allows me to have larger ping sizes, so I can reduce the degree of how accurate it can be, or can make it more accurate by having a larger ping size being used for the samples. So get a larger range of delta latencies, or more precise delta latencies with those larger ping sizes. That looks pretty good for the moment. So we're getting a ping result, and that'll be useful for carrying on with this project.